In the previous lecture, we have discussed about the binomial theorem for any given index n. So here n could assume any real number. So it could be a fractional number, it could be a rational number. So the expansion of 1 plus x raised to the power n was proved by using the Maclaurin series, which is given by summation r going from 0 to infinity and cr times x raised to the power of r. And when we expand this series, we get 1 plus nx plus n minus 1 over 2 factorial times x squared, and so on. Now the general term of this expression is given by tr plus 1 equals to n minus 1 times n minus 2 all the way up to n minus r plus 1 divided by r factorial times x raised to the power of r. Now here, while doing this derivation, I didn't discuss much about how the final term, which is n minus r plus 1, was obtained. So let me give you a quick help. So the first term, which is n, can be written as n minus 0. The second term will be n minus 1. The third term will be n minus 2. Now we have to predict what is the general rth term going to be. So n minus the rth term going to be here. So the rth term can be obtained by using the formula a plus r minus 1 d. That's because we can see that the first value is 0 followed by 1, then 2, all the way up to the r terms. Now here this is an AP series, arithmetic progression. So we can use the formula to find the term, the general term. So that would give us the first term is 0 plus r minus 1 times the common difference, which is 1. So common difference can be found out by subtracting the first term from the second term. So 1 minus 0 gives us 1. So that gives us a general rth value, which is r minus 1. That is what we're going to replace here. And we should get n minus 0, n minus 1, n minus 2, all the way up to n minus r minus 1. So that is how we got the general term in the numerator, the general expression in the numerator, which is n minus 1 times n minus 2 all the way up to n minus r plus 1. Now that we've understood how the general expansion of a binomial expression 1 plus x raised to the power any index n is given, now we are going to look at a more general case. So what we're going to do is, if you're given a binomial expression x plus a raised to the power of n, where n is any rational index, write it down, n is any rational index then how is the expansion of this given binomial expression would look like? So the first one, the first case number A that we're considering here is if the absolute value of x is greater than the absolute value of a. Then in this case, what we have to do is we have to simplify. So let's do some simplification here. X plus a raised to the power of n. So we are going to factor out x. So that will leave us with 1 plus a over x raised to the power of n, which can be rewritten as x raised to the power of n 1 plus a over x raised to the power of n. Now we're going to apply the binomial theorem, which will be x raised to the power of n times 1 plus n times a over x plus n times n minus 1 over 2 factorial times a over x whole squared, and so on. After that, we can multiply at the later stage x raised to the power. For the time being, we're going to keep it as the way it is. So x plus a, the expansion of x plus a raised to the power of any index is given by this particular expression, or this particular form. Now here, this will be the expansion is in the decreasing powers of x. Meaning, if we look at the second term, so the second term, now let's not consider the n value and the a value. So we have 1 over x in the second term, and in the third term we have 1 over x squared, in the third term 1 over x cubed, and so forth, and the nth term will be 1 over x raised to the power of n. So when we take the x to the denominator, to the numerator from the denominator, we get x inverse x raised to the power of minus 2, x raised to the power of minus 3, all the way up to x raised to the power of negative n. So here we say it's decreasing. The powers of x is decreasing. So that's what I meant to say. It's written in the form of decreasing powers of x. So this happens when the absolute value of x becomes greater than the absolute value of a. Now we go to the second case. Now in the second case, we will consider that case number 2. We'll consider that the absolute value of x this time is less than the absolute value of a. Then our binomial expression x plus a raised to the power of n. Now what we're going to do, now the manipulation will look, so we are going to factor out a this time. So this will leave us with 1 plus x over a raised to the power, whole raised to the power of n. Now we take out the first value, a raised to the power of n, times 1 plus x over a whole raised to the power of n. Then we expand the binomial expression. That should give us 1 plus n x over a plus n times n minus 1 over 2 factorial times x over a whole square, and so on. So if we look at the second term, so we have x in the numerator. Then we go look at the third term, we have x squared. So the fourth term will be x cubed, and the nth term will be x to the power of n. So this would mean that the nth term will be n minus 1, using the same logic that we used previously. So the nth term will have the index n minus 1. So here we have seen that the powers of x are in the increasing order. So when we have this condition of the absolute value of x less than the absolute value of a, so we get in the ascending order of or ascending powers of x. So now we talk a little bit about the difference between the binomial theorem when n is a positive integer and when n is a general exponent. So we have talked about the expansion of 1 plus x raised to the power of n when n is both a positive index as well as any general index. So there are some remarks that I would like to make. So if n is positive, then the number of terms in the expansion of 1 plus x raised to the power of n will be n plus 1. However, if n is a general index. General is to say if it's a real number. If n is a real number, then the number of terms are going to be infinite. There will be infinite number of terms. So that's the first conclusion that we can draw from the binomial expression 1 plus x raised to the power of n. The second one is if n is positive index, when n is a positive index, our expansion, the expansion of 1 plus x raised to the power of the positive index n is valid for all values of x. While in the case of n being a general index, then the expansion holds. The expansion of one plus x raised to the power of n holds when the absolute value of x is less than 1, because this is the only time when the expansion is going to converge. The third conclusion that we can draw is that in the expansion of 1 plus x raised to the power of n, when n is a positive index, then the exact value of 1 plus x raised to the power of n can be obtained by adding up n plus 1 terms, while in the case of if n is a general index, we never get an exact value. We will get only an approximate value when it's calculated up to a finite number of terms. Now this comes from the conclusion number 1. We have seen that if n is a general index, that's a real number, then the number of terms are going to be infinite. So we cannot add infinite number of terms. So however, what we can do, we can take some finite number of terms, we can add the term, and that is going to give a somewhat an approximate value. It's never going to be an exact value, but it will be closer to the exact value. So while if n is a general index, the value will be if n is a general index, then the value of the value of 1 plus x raised to the power of n can be obtained approximately by adding finite number of terms. So we'll be doing more numericals based on all the drawn conclusions and for all the expressions that we have discussed for the different cases. As in when the absolute value of x is greater than the absolute value of a, or the absolute value of x is lesser than the absolute value of a. And all the three conclusions that we have drawn from the expansion of 1 plus x raised to the power of n, all the three conclusions, we're going to use it and we're going to understand more on the binomial theorem.